Hello and welcome to the podcast According to Sci-Faith, where we discuss topics revolving around the compatibility of science and faith. I'm Joshua Göcking and you're listening to According to Sci-Faith. Preview of the episodes 21 to 24, What is Truth? Episode 21, Holographic Duality. So, as you remember, in one of the last episodes we were talking about quantum gravity and what the issue with quantizing gravity is, which issues to occur there, what are the problems, why do we not have yet an established theory of quantum gravity. And what we saw there was that there is, as in particle theories, you always have these exchange particles who mediate the forces that are occurring on a particle basis, and the exchange particle for gravity would need to be so heavy that in this area where this particle would be, a black hole would be created. And black holes are difficult in the sense that they cannot be described completely because they are a singularity. So something tends to go to infinity there, and this always means that you cannot really describe it because we cannot describe infinities. We cannot calculate really with infinities, and this makes it really difficult, or this makes us lose the predictability and the describability in these theories, which is not really helpful for us. And therefore, we are looking for solutions, and physicists are looking for solutions there. And there's this one concept that might help there, and this is the concept of duality or holographic duality. And that's what we want to look into further in this episode. So, and this is also closely connected to black holes. So we will first start by considering black holes in a deeper sense, considering what those are, how they can be described, and what are the specifics of black holes without diving too deep into mathematical issues and so on. But I think there are some simple facts about black holes one should know. So for once, there is this thing of an event or horizon, it is called. This is basically a radius, or okay, let me say it like this. So if you solve the Einstein's field equations, which are the equations of general relativity, then you get one of the solutions you can get there is the so-called Schwarzschild solution. And this solution has a so-called Schwarzschild radius. And what this radius basically describes is the radius at which, if you go beyond that radius, then you cannot flee from there. So you cannot get out of it anymore, even if you are as fast as light. So even light cannot come out of the space that is lower than this radius. And so this the sphere that is built by this radius is called the event horizon. So beyond this event horizon, nothing can get out. Nothing can get out anymore. And once you're in a black hole close to this event horizon, and you even go beyond it, then you can impossibly get out of it again, and you are lost forever, so to speak. And that's also why the black holes are called black holes, because they are black to us. We cannot see beyond this event horizon. We cannot see what's behind it, because even light cannot get out of it. So this is one of the key facts about black holes, one of the defining characters of a black hole. And there's also one more defining character of a black hole, and that's the so-called no-hair theorem. And this states that there is nothing more than mass, charge, and angular momentum that can describe a black hole. So there are different kinds of black holes. So all black holes do have a mass. That's what they all have, because they are objects with a high gravity. So of course they will have high masses. But in principle, black holes also can have a charge. and they also can have angular momentum. But those three properties completely describe any black hole. This is the no-hair theorem, and the name no-hair theorem means basically there is nothing special, no hairs. There's nothing more than these three properties to describe a black hole, which is different from any other spherical objects like planets or stars, where there are a lot of things that can describe these things. For example, if you just take Earth, there are living beings that are on there. There is water, there are different elements and so on. There are many properties with which you can describe Earth, but for a black hole we say no, there are only three properties which completely describe a black hole. But this leads to a problem, because if we now take, for example, two black holes and we merge them together, then if we go to according to the laws of physics with this no-hair theorem, we should not increase the entropy of this system. And this is really a problem, because the second law of thermodynamics states that the entropy of the universe basically is always increasing. So the overall entropy of a system is always increasing. So now you might ask, what is the entropy? What is that? What is this thing? And this is basically a quantity that measures the disorder of a system, you can say. So disorder is not necessarily how you might think of it in a classical way, or how you might think of it in your own life, or in like a disordered room or something. No, it's more like the kind of way in which physics work, that everything goes from an order state more and more into a disordered state, meaning that basically if you have, for example, you have a box and there is a gas. So the box is separated, there's a wall between it, so it's two spaces, and in one of those is a gas, and in the other there's, for example, a vacuum. And if you pull the wall out of it, then the gas will, after a certain time, have filled the whole space. So from the ordered state where it was only in one area of this whole box, it has filled the complete area into, so it all of the box has become disordered in this way. So this is kind of what you can think of as entropy, that this tendency of particles and of the whole universe, or everything in this universe basically, to move to a state of more disorder. And this is a law that is pretty well established, and if this is not true in some sense, then physicists know there must something not be right, because as you can see, this also is responsible for the arrow of time, basically for the irreversibility of time. So basically that if once you have this box and you have removed the wall, it won't happen that the gas, once it has spread out into all of the box, that it will move back to the reduced area. This just won't happen. And similarly, many things will not reverse itself. For example, if you have a vase and it falls on the ground, then it will split into all kinds of it will be destroyed, but it won't fall back up and get nice again. So this is kind of also related to entropy, and this leads to time moving in an irreversible way, so that as you know from relativity, time is just a dimension as space. But in contrast to space, where you can go forward and backwards, you cannot go backwards in time unless you are in some science fiction movie. So this is kind of, and the reason for this is to some degree at least to be found in entropy. So the problem here is that seemingly around with black holes, this entropy doesn't seem to increase. So there has to be a solution for that. And actually, among other physicists, Hawking found a solution for it. And what he was doing is he defined entropy in regards to the area of the black hole. So in in this case, the entropy of the black hole increases as the area of the black hole increases. And so when you merge those black holes together, they will increase in the area. So not they will increase in the area, but basically the event horizon will increase in its area. And then this will mean that the entropy has increased. So what's interesting about that is if you look at it now from a dimensional perspective, as I showed you with the box and where the gases were in it, the entropy increases by the gas increasing in the box, and this is an increase in volume. So the box has its volume, and if I put the wall away, then there's more volume to be attained, and the gas spreads out in there. So an increase in entropy in this case is an increase in volume, and usually in physics it's always this way that the entropy increases because the volume increases, or you get what I mean now, I hope. But in the case of the black hole, this is different. In the case of the black hole, it increases as the area increases. So the entropy increases with the area of the event horizon, not the volume of the sphere of the event horizon, but of the area. It's proportional to its area, where it in other cases is proportional to its volume. And so if you now look at it, okay, an area is a two-dimensional object. If you just draw out an area of a square, it will be two-dimensional. You can put it on a sheet of paper, so it will be two-dimensional. And but a volume is always a three-dimensional object. If I was talking about a box, so you can think this box is basically a cube. So that's a three-dimensional object. So what I have here is that the same property or the same occurrence is of entropy in our physical world is one dimension lower in this black hole world. So in this area of the black hole. So it's like one dimension has been reduced. Another question is does this hold in general? Is there a general rule where I can say that some properties of our physical universe are like one dimension less if I look at it from another perspective or in another realm? So, and this is indeed the case, and that's what called the anti-de Sitter conformal field theory correspondence, or for short, oftentimes ADS/CFT correspondence, and that's also what we mean by holographic duality. And this is what we want to look at into a bit. So we were talking, I think, in one of these last episodes, we were talking about quantum field theories, because those are the theories that describes the physics at a particle level, and I think there we especially described the theory of the weak force, because this was created in a similar way as we tried to create our theory of quantum gravity. But now we want to look deeper into what how these theories in particle physics really work, especially how the forces are established there. So basically we have different kinds of fields in quantum field theory. There are scalar fields like the Higgs field, or there are spin fields like photons and exchange bosons, which are mediators of this force that we are looking to now. And then, of course, you have the spin half particles like electrons and so on, which are part of matter. But we will look into these spin one particle fields, and they are mediated by symmetry groups or by gauge symmetry groups, gauge symmetries. You don't really have to understand what this means, but basically what it does is, so there are these symmetry groups that you can have, and they are of a certain properties. So I just will name them. So there's the U1 symmetry, the SU2 symmetry, and the SU3 symmetry. Those are the symmetries with which our particle physics theories are described by now. So the U1 symmetry you can, for example, use to describe the electromagnetic force. And this is done by, so U1 means 1 is the dimension of this group. So it's not the physical dimension, it's the dimension in which this group is described. You can see the one dimensionality of this is the fact that the electromagnetic force has only one charge. So you might say, hey, it has two charges, plus and minus, but this is basically just one expression of one charge. So plus is one expression of the electromagnetic charge, and minus is the opposite expression of this charge. So, but actually it's one charge, and that's why this is a U1 symmetry. And the U or is for unitary group. So you don't really need to know what this means. This is just some way the operations are made there with some symmetries that this obeys and so on. And this is basically what basically happens if you add such a symmetry term to the equations of particle physics, then you get an interaction term, and this interaction term basically describes the electromagnetic forces. But as we have seen, there are more forces than that. There's, for example, the weak force, that we described also in the earlier episode, for that is responsible, for example, for radioactive decay. And as it turns out, you cannot really describe this force in and of itself, but you have to combine it with the electromagnetic force, and together you get the U1 SU2 symmetry, which is describes the electroweak interaction. So it describes the electromagnetic interactions and also the electroweak interactions, where you get the gauge bosons, the W and the Z boson, which are the only massive gauge bosons, but that's a whole different story. And those you get from the symmetry group. And as you have heard, there's the SU2, which means that there are, this is a two-dimensional, it's a two-dimensional group, and therefore you also have more gauge bosons, and this is also, you have kind of more charges, they are described differently there. And then you have also the strong force. The strong force is described by the SU3. It's the three-dimensional group, unitary group, and here it is the case that you have you have three charges. So you have the color charges. I think we described that once. So they are given by three colors: red, green, blue. So those are not colors in the classical sense, so they have no color like you know them to, but it's just a way of describing these different charges. And you might think, oh, now it's three charges, before it were two, where you said that it's actually one. No, here it's the same case, because they are also anti-color, so to speak. There is the color charge of anti-red, anti-green, and anti-blue. Might not make sense in any way, but I mean, in colors you can also have a similar way where you have an anti-color, but I'm not gonna dive deeper into that. So what this is, it shows basically how you can describe these forces using these symmetry groups. And this has been a pretty successful approach in describing these interactions at a particle level. And this has made people come to the conclusion, hey, maybe if we want to combine these forces to one, as you have seen, we can combine the electromagnetic force and the weak force, we can combine them to one force, and the idea is that we can do this with all the forces, that they all are part of one unitary force at one scale. And this is going with the term great unified theories. And if you also look at the couplings of these forces, you can see that there might be a point where they all have the same value, and this is also part of ongoing research. And the idea is that these SU groups might be really helpful, these special unitary groups might be really helpful in describing such an interaction, and maybe even describing the interaction or unifying the interaction at once. And what is then interesting in the regard that we are looking is if we generalize these groups to the so-called SUN. So we take not some number, we generalize it to a number n, and then we use this number and we let it become really big. So we take n to infinity, and then we look what happens there. And as we can see, if we look closer into what happens there, then we can see that there is a further dimension in those really large matrices. So these groups, these symmetry groups, are described by matrices, which are mathematical objects. You don't need to understand what those are if you are not familiar with them. But if they all have their dimensionality, as I told you. U1 is one-dimensional; it's basically a number. SU2 is a 2x2 matrix, and so on. And if you go to n really big, then there you see that there is a further dimension that is kind of built into these matrices. And how you can imagine this, or how you can illustrate this, is basically, for example, if you have in one dimension you have a scale where you, for example, you can have either particles arranged in a circle of 1 centimeter, or you can have them arranged in a circle of 10 centimeters. This scaling corresponds to an own dimension in this anti-de Sitter space that you can have. And this is a really interesting feature, that you can have what in one space is just some scale or something similar to that, can be in an own dimension in this anti-de Sitter space. And for example, you can also have, if you have a gas in this, let's call it normal space, you have a gas with a high temperature, and what you know physically, temperature means that the particles in this gas are really quick in quick motion, so with high velocities. And this would, in this anti-de Sitter space, this would correspond to a black hole at some point in this anti-de Sitter space. And this is basically this holographic duality, that you have this duality, and in this way you can also describe black holes as a hot gas of particles in this, if you take it into this other space. The problem here is that we do not live in this anti-de Sitter space. So what the anti-de Sitter space is, I just mentioned it without really defining it, but the anti-de Sitter space is, so you have to imagine, from general relativity, we know that our space is not flat space. It's not like flat space basically, but it's curved, and that's the whole thing of general relativity, that we say space is curved, and this leads to gravitational effects and so on. And this curved space can be positive or it can be negative in principle. And the anti-de Sitter space has a negative curvature, but our space, the space in which we live, has a positive curvature. So we do not live in anti-de Sitter space, but we do live in de Sitter space. So that's the problem, and that's why this duality does not really work for us, because we are kind of have this duality to the wrong space, so to speak. And therefore, you can kind of say that quantum gravity theories in some sense are similar to particle physics theories, but one dimension lower, and also with opposite curvature. So it's still there you still see a problem with this, that it's basically the wrong room to which this duality exists. And that's why it's still very theoretical and still a part of ongoing research. But it's really promising, because this would really be helpful in describing black holes and these objects of general relativity, where we have problems to describe them, and also problems to unify them to our theories, and problems to find a unified theories of quantum mechanics and gravity. So I think we can also describe this in a spiritual way, or we can find a spiritual interpretation for this. And I think that we can see from that there are, first of all, we can of course see that there are different description of theories. So you can either describe something like a quantum gravity theory with black holes and so on, like in this anti-de Sitter space. You can describe him as such, and there you will have one higher dimension, or you can describe it as the particle physics theories that we are familiar with, where you have one dimension lower. So this shows you that there are different ways to describe a theory and also to interpret a theory, as we have oftentimes discussed on this podcast in terms of Sci-Faith, that there are always different ways to interpret and describe the physical facts that we know. And what it also shows to me, I think, is many things of the supernatural. So first of all, I really believe that there is a supernatural world. There is something beyond this material, physical world. But many things of the supernatural can also be explained kind of in a natural way, can be explained by natural means and so on. But then we do not get the full picture, and it's kind of going one dimension below, so going one dimension lower, and missing kind of the full picture, missing everything, because in the higher picture you have stuff like black holes and so on that you cannot really describe, and in this lower dimension you might be able to describe everything, but you're kind of in the wrong room, you're kind of in a wrong space in this picture, and kind of in one dimension lower, and you cannot really get the full picture, you cannot grasp it all. And I think this is similar. If you really just look at the world in a material way, you may be able to describe a lot of things or find a description for many things, but still there is something missing. You do not get the whole picture. There are just some parts missing, and I think this is a great illustration of that, and therefore I think it is really important and necessary to really focus on also what's beyond the material, what's beyond this materialistic world, and to really get a grasp of that, even if we cannot completely understand it, but still understand it in the way that we need to, and get a grasp of that, because otherwise we will miss it. Episode 22, Fundamental Research, Quo Vadis. So recently CERN announced their plans for a new particle collider. They called it the FCC, or Future Circular Collider, and they have pretty ambitious plans for it. They are planning as the name says, a circular collider. So they wanted to collide the particles in a circle. The circle should have a circumference of 91 kilometers, and it is supposed to be 200 meters beyond underground. And the energies they are trying to achieve are 100 tera electron volts. So to compare it with their currently LHC, which is currently, I think, the biggest machine that biggest particle collider they are using, or generally the tallest particle collider in the world. There they have about 27 kilometers circumference, and it's about 80 meters deep underground, and they achieve energies of about 14 tera electron volts. So it's about three times larger. And what they are planning to do is, at first they want to have it built by the 2040s, and then they want to start with electron-positron collisions. And the reason for that is that they are much cleaner. This is because those are really fundamental particles, so you know the energy that is going in, and you don't have a lot of particles flowing around that mess up your experiment and that are just useless background that you have eliminate from that. So it's much cleaner, and this allows you to study the properties of the particles you want to investigate much further. And the goal of this is especially to study the Higgs much deeper. So as you might know, the LHC, the Large Hadron Collider, was its great discovery was the discovery of the Higgs particle in 2012, and since then, they were researching the Higgs particle. Of course, they were also looking into other things, but mostly they were trying to get more information about this Higgs, more part of the properties, how strong are the couplings to other particles, in which particles does it decay, and so on, to really nail down all the specifics of this Higgs particle. And they want to nail it down even more because they want to really get an understanding of how this particle behaves, how it works, because there are before it was discovered, there were different theories of how this particle is supposed to be or could be, and the result was a little bit different what any of these theories expected. And now one wants really to find out the specifics of this particle, and also what other properties what one might not yet have found this particle obtains. So once they have done this, they want to start to do, as they do now at the Large Hadron Collider, hadron-to-hadron collisions, like protons, for example. And with this, the goal is less to really be precise about the properties of certain known particles, like the Higgs boson. Now with this approach, they really want to find new particles like dark matter particles, or they want to find what's behind dark energy, or all these unresolved questions that are currently still open in physics. They really want to dive deeper into that and maybe find this so-called new physics. And this is the strategy between this second run, or the second implementation of this collider. And this might sound odd, but basically that's really the strategy, how they used to do it, how they did it with the Large Hadron Collider. There they also first used it with leptons, so like electrons and positrons, to really make precise measurements about the particles that were already known, like the W boson and the Z boson, to really nail down the specific data for the specific particle data of these particles. And once they were pretty sure about those, they started to do hadron-hadron collisions to discover the new particle, the Higgs boson. And this is how it is usually done, and this is a pretty reasonable approach. And also just the reason why one does this, or why one measurement is finer and one is more clean and one is more rough and not so clean, is so, as I have already mentioned, for electrons or for leptons, like the electrons that you use for these cleaner experiments, you really know the energy of the particle in the beginning, and you know therefore exactly the energies, and you don't have other particles flowing around that mess up your experiment, or that are unnecessary background that you have to reduce afterwards. So the question might be, but why then would you do hadron-hadron collisions if electrons are so nice? Well, it turns out it is not as nice as you might want it, because one disadvantage of using electrons is that they are, a lot of the energy that you put into these electrons will go into so-called synchrotron radiation. So this is radiation that comes from basically is an effect of Bremsstrahlung. So Bremsstrahlung is what occurs if a charged particle is accelerated or decelerated, and then it will radiate. It will give off light. It will radiate light, So that's what will happen, and this light of course is energetic, and this will lead to the energy that is used for accelerating the particle will be to some degree lost in this radiation. And the more you accelerate, the less you get out of it, because a lot of this energy that you use to accelerate a particle will not go to further accelerate it actually, but will go into this radiation. And then you, for one thing, you waste a lot of energy, and for the other thing, this radiation will be in your detector, so this will fly around, and you will also have a lot of background from that. So that's not really what you would like. And as it turns out, this synchrotron radiation is proportional or anti-proportional to the mass of the particle. This means the heavier the particle is, the less of this radiation you have. And that's not just linearly, this is really to the power of 4. So it's really, if the particle is twice as heavy, it will be to the power of 4 less radiation. So by decreasing the mass of these particles already a little, you will already achieve a great effect. And therefore, hadrons are really popular in this regard, because they are a lot heavier than electrons. So the proton is a lot heavier than an electron. So therefore, you use those. And also one reason is that the hadrons, of course, they take a part in the strong interactions, which also makes the experience messier, but it also allows for more particle reactions, or potentially more reactions or more decay channels and so on. So it's a lot more messy, but you cannot get a lot more out of it, and the energy you put into them is directly going into the particles, but it does not go all into the particle you want. So as I have mentioned, hadrons are not fundamental particles. They consist of 3 quarks, or 2 quarks if they are mesons, but usually you use hadrons or baryons like protons who consist of 3 quarks. And these, if I now accelerate them, of course, all these 3 quarks are accelerated. And actually, the picture is a little more complicated, because there are not only these 3 quarks, but these quarks bind together with gluons, which are the exchange particles of the strong force. And furthermore, there are these so-called C quarks. So since there are all kind of quantum fluctuations in these hadrons, then there, additionally to these 3 so-called valence quarks, there are C quarks who are just pop out through these vacuum fluctuations basically. So you have a lot of particles basically already in there, and depending on the energy of the particle, you have more C quarks or more or the valence quarks will be more energetic. It depends on how energetic they are, and this cannot be described analytically. This can only be described by measurements, and there are the so-called parton distribution functions who describe the energy composition of these hadrons. And what makes it harder, of course, is if I now have a process where from this hadron who are colliding, one of the quarks is reacting with one of the other quarks, and there's one process I would like to see and I would like to analyze it. It's of course important to know how much energy went in there in order to know how much energy went out of it, so to calculate it accurately. But this is here not completely possible, since I only know the energy of the hadron and not the energy of the individual quarks. This I can only estimate by using these parton distribution functions. So as you can see, there's a lot of inaccuracy coming in there by not really knowing how much energy the particles that react with each other have, and also of course the other particles that flying around, they are just watching as the reaction happens. That's why they called spectator quarks, and they might even react in another process or do something else and just mess up my detection. So they are just useless background. So there's a lot of background that I have to eliminate afterwards, and a lot of other stuff, and this is is difficult to, but there are, by now physicists have come up with really good techniques to remove that, but it's still a challenging thing, and therefore it is really messy, but it also allows for processes that otherwise would not have occurred to come up or to be observed, and therefore it's really still interesting to use this, or still really helpful to use this to find new physics. So this is what they proposed. This is what they want to do in Geneva, where they are located, and there are also, so there are different reactions to that. Some have criticized it, some are really in favor of it. But first, before we look into that, I want to look into possible alternatives that have been proposed, and one of the most popular alternatives proposed to it is that of a so-called muon collider. And muons are particles basically like electrons. Actually, you can think of a muon like a really, really heavy electron. That's basically what it is. So there is not much that changes, only that in contrast to electrons, muons do not live forever. They decay pretty fast, actually, in a matter of microseconds. So on a particle physics level, that's still very long, but for us it seems pretty short. But there is, of course, a workaround, but I will get to that in a bit. Just first, I want to mention the real advantage that such an collider might have. And you might have guessed it already, because I said it before, that the problem with a collider of electrons is really that this fact of synchrotron radiation occurring, and this is a real issue. And as I said, the muon is much heavier than the electron, and this will lead to a reduction in the synchrotron radiation. Even it's a billion times reduced radiation by using muons. So this is a real big advantage, and so it kind of is you get the best of both worlds. So you do not lose that much energy into synchrotron radiation by using muons, but also you have a clean setup. You don't have this messy hadron stuff where all these jets and stuff is flowing around, but you have really just clean particles, and basically have the advantages of the electrons without the disadvantage of this synchrotron radiation. So that's the idea behind it. But now I already mentioned the problem that you would have with muons, and that's the fact that they are decaying. So muons decay in about microseconds. So what's how can you prevent that? So you would really need to be fast in accelerating them. So you need to be really fast in accelerating them to high speeds, and then you get this great relativistic feature, because if I tell you now that every second there are a bunch of muons flying through you from cosmic radiation, that would be true. But you might ask, how can this be if they are so short-lived? And actually, it's this way, that if you know it from the theory of relativity, then you know that time depends on the frame of reference that you are in. So in the frame of reference of the muon, it really is that short-lived and decays after those microseconds. But if it is really coming with the high speeds, with relativistically high speeds, then in the frame of reference of somebody who is not moving at that speed, it is a lot more time passes in these microseconds in the frame of reference of the muon where it decays. So therefore, the muons that are traveling to Earth really reach Earth without decaying, because in our frame of reference, their decay time is a lot longer. And if you manage to accelerate these muons pretty fast to high relativistic speeds, you can use this same effect. But still, there will be muons that will decay in the detector, that will decay in the while you collide these particles. And they, of course, these decay products, those are electrons and neutrinos, so you don't need to worry about the neutrinos because your detector cannot see them anyway. But the electrons you need to worry about because they will be visible in the detector, and then they will be background because you know for sure that they are not part of the process that you are looking into. And so you need to separate them somehow. So this is a challenge that you have with muon detectors. So first of all, you need to take care that not too many of the muons you have in your detector will decay prematurely, and also you need to make sure that the muons that do decay and that want to mess up your experiment, their background, that you eliminate this background properly to not get mixed it up in your results. So also there are really issues with this approach. Those are some of the proposed particle colliders. There's also there are also proposals to use linear colliders. Those have the advantage that you can gradually expand them, with a circular collider you of course only can use them once the circle is completed. With a linear collider you can expand them as you go on. This is one of the arguments presented there. But still there's a lot of critique to this circular collider. For once, many criticize that there are no clear goals that this collider has. So, for example, the LHC already also promised that they might find dark matter or some new physics, which it turned out they really didn't. And so there is this meme going through social media or through physics social media. So yeah, just one more collider, just one more billions to spend, and then we will know dark matter and all the stuff and new physics and so on. So just making this argument that it's just one more of those billion of dollars that they spend, and especially many from other fields than particle physics really criticize that there's a lot of grants going into this area of research where others really lack those magnificent grants. And so there is a lot of discussion about this, and also about a real purpose of this, which aims are to be achieved by that, and also coming from mostly non-scientific areas is of course the question, okay, what does this at all serve for? How does it help society or technology or whomever to know that there's a Higgs particle? So until now there is no real technological use for these particles or to be found in there. So, and what the argument always is that it might not be useful to know that there is a Higgs particle or there are these W and Z bosons. Those might not be of technological use, at least not in the short term. But what the discoveries along the way might really be helpful in this way. For example, it is often argued that the internet itself was discovered at CERN. So there was Tim Berners-Lee was working at CERN, and he found a way for them to share their data more effectively, and this was basically the internet that he created there. And also what I heard once, an argument that they had at CERN, this so-called grid, they called it, where they also shared their data with each other. And this was basically a version of the cloud, which was later, of course, became pretty popular. And then, of course, in the medicinal area, there's in radiation therapy and many other areas, much of what is used there are discoveries that came from particle physics or from this research in collider physics and so on. So there are many progress has been made by just these side discoveries. But one might argue, wouldn't that have come about anyway, or would you have not, if you would researched directly in this way, have come up with these solutions without spending that much money? Or whatever the arguments might be. So there's an ongoing discussion about this, and also among physicists there's an ongoing discussion. There it is more in a way, if are there not cheaper experiments or more economic experiments that would lead to similar results? Does it need to be this bigger, better, greater particle collider, or are there maybe other ways to find out more? And even if one uses these colliders, does it need to be or shouldn't it be there be more specific goals that one has? Shouldn't it be more specific than, we will find something maybe, or so on? So I think there are many points of critique, but also many as I have presented, many things that are in favor of it, especially even if there are no direct discoveries, the discoveries that are made on the way. So just kind of, it's about the friends you are making on the way. So there are, I think, arguments in pro and in contra, but it stirred, I think, so as I saw it, it stirred up a discussion among scientists, but also among non-scientists about the purpose of all this. And I think it's also, to me, illuminating kind of the question of that's also in the title of this episode of science at all. So what really is the purpose of science? What is the goal of science, or not science in itself, but of this kind of science, of this foundational science, of this foundational kind of science, and fundamental science, fundamental physics, fundamentals research. What is the goal of it, or where does it go? Where does it lead? And I think one of the issues is that we are coming to a point, especially in this area, where one needs to really decide if one wants to go in a way where we just argue in a materialistic way, or where we just go beyond that, or just accept that there might be something beyond that. Because many of these areas of foundational research, maybe not in the particle physics area, but in other areas, is coming to points where you really see there might be an argument that this is probably not just to be described in a physical manner, not just to be described in physics. For example, if we talk about consciousness, we had it in the last week several times on this podcast about consciousness, and the pretty strong argument, in my opinion, that there might be more to it than just the scientific processes that are occurring, or the materialistic processes that are occurring in the brain, that there might be a spiritual component to that. Even if you do not believe it, you must leave room for the possibility that might be the case. And also, if we go back to particle physics, there you also see this occurring, that there might be this, since particle physics, in many ways, the processes we observe there should describe what happened in the beginning of the universe, after the Big Bang, and so on. There is still the big argument that this was not a completely naturalistic process, but that there might have been divine interaction and so on. So I think this cannot be completely ruled out. I'm not arguing in favor of kind of describing this scientifically or something like that, because that wouldn't be scientific anymore by definition. But I think there is a point being reached where one must accept that there might be out the answers of this might lay beyond the area of science, beyond the realm of science, and that there might be a border up to which science can go. As I have mentioned in an earlier episode, I don't say that science is at an end with that, but that there is a border where science itself cannot describe the whole picture. And I think if we do not acknowledge that, then at some point it just comes to playing around with theories, with experiments, and this just one bigger collider, just one more, just this grand, and this use this, and so on. And this is just, I think, at some point it gets too much of just trying to prove stuff or trying to find stuff, where the actual solution would be to go beyond what, or to accept that there may be something beyond science. And I think also what this meme of just one more collider, just one more experiment, and so I think what the critique point behind this also is of course that there seems to be lacking a philosophy behind that, a philosophy behind the why of the why do we need those colliders, why do we use this, why do we do it like that. And I think the critique point is also, in my opinion, valid, because in some sense you do not really get the philosophy behind it, the idea behind it, the reasoning behind it. And I think this is also what seems to be missing in science in some ways, that it's really just this materialistic describing of things and not going deeper. What is the philosophy behind it? Why do we do this, or what is our goal with this? And this is also what in the next episode I want to dive deeper into the philosophy of science, or what comes first, philosophy or science, and how do they work together. Okay, it's time for a short break. We will continue in a bit. As you know, my book is still available on Amazon as an ebook, of course. And there's great news, because in the last months I was already reviewing parts of the book and already updating it or re-editing it. So there's a new version out there now where some minor errors that came up, typos and so on, were fixed. So if you want to read it, now is the perfect time to get the new version, the updated version. If you have already bought it, you of course can re-download it, since it's an ebook. That's the advantage of it, and you will also get the latest version. So I encourage you to do so. If you have not read it yet, I really encourage you to get it, because many of the things we talk about here in Sci-Faith are in this book, and also more things than that. And it's really packed in an entertaining story. On the German version of the book, so in Amazon, there was already a review, and it was really a really good review. He really liked the book, and so if you have read the book and you want to give a review, or want to show what you thought of it, I really would appreciate it. It really helps and supports others who think about buying the book, and it helps them to see if the book is something for them. So please do so, and I really appreciate your support. Also, if you want to learn more about Sci-Faith, I really encourage you to look to my webpage. There you can find out more. Also on my Substack, there are regularly Substack blog posts appearing where you can read more about Sci-Faith, more about the ideas behind it, and articles about it. And also you can subscribe to my newsletter, where you will be updated with what's happening on Sci-Faith, and you will always receive the latest blog post in your email. So it's a great way to keep up to track what's going on in Sci-Faith, so please do so. And also, if you have not read my book about Sci-Faith yet, then I really encourage you to do so, to read it, because there I really go into the depth of science and faith and how all this can work together. So I really encourage you to read it, because this will really give you a deeper understanding of how science and faith can work together, and how they are not incompatible at all. So with these announcements, we go back to the podcast episode. Episode 23. What comes first, philosophy or science? So in society, you often talk about this fact that politics and culture seem to be influencing each other, and depending on which culture you live in, this will affect the politics that is occurring in your country, and also vice versa. So what I was asking myself is, or what I recently realized is, that a similar effect is occurring in science regarding philosophy. So the philosophies that are around in some area or in the mind of people oftentimes affect the science that is being done, and oftentimes even affect if there is something as science being done, or if science cannot occur because the philosophies are not well enough or something like that. And this we want to dive deeper into in this episode. And first of all, we want to show that basically really philosophy played a huge role in the coming up of the scientists with the scientific method. And this can be seen by Newton, who believed in a creator who had a personality, and with this personality he believed there comes principles, and from this principles he concluded that there are nature laws of nature. So I mean, to us, if we study physics, if we know physics from school or where we came into touch with it, for us it's pretty much common sense that there are laws of nature, but this has not always been the case. So before the scientific method was developed, people thought all different kinds of things. So there was, especially about universal physical laws, that there was no common ground that this should be the case. So people believed that the laws that describe what's happening here on Earth should be or might be different from those that are ruling what happens in space. And so there was no idea of universality of universal laws of nature. And so what Newton did, it was not just something that was common sense and he was the first one to formulate it. It was really a big step in the understanding of nature. And I think, especially if you read about him and if you look how in his Principia, especially in his great scholium, how he argues his natural laws and so on, then you really see that this conviction that there have to be natural laws that describe nature, this really comes from a belief in a creator who obeys principles, and who therefore whose creation therefore also will obey such principles, which we today know as natural law. In a similar way, you can find it for other founders of the scientific method. For example, Kepler, he believed in a God of order, and this you can clearly see in his Kepler laws, who are really laws of the order of the universe, of the planetary motion, and so on. So you see that this philosophy that the first scientists or the first scientists of the modern era had has really impacted the way they interpreted science, the way they came up with their scientific theories. So there you clearly see that philosophy impacts science and impacts the scientific ideas and the scientific theories. And this is not a problem, this is just a simple fact. And especially when the philosophies are good and are right, this seems to be pretty helpful or pretty useful, because if you think about it, so the scientific method really ushered in this scientific revolution that we talk about, where in about the 1700s it began with these scientific findings that arrived every 25 years or so. You had a new scientific finding, which is pretty astounding, a pretty astounding fact. And this was not the case before, and there was also some kind of science before, but this methodology that was developed later, this was not there yet. This wasn't also with the ancient Greeks, this was not there yet, and that this was developed, it was pretty helpful for science to really come this far, and it was really at the core of it was a philosophy that really believed in these key facts that allowed for the development of natural laws and and these theories and the methodology to prove these theories or to try to confirm these theories. But there's also this also shows, okay, if the philosophy is good, then this might lead to good science, to good scientific ideas. But of course, you can also see that if the philosophy is not so good, or if it's wrong philosophy, then this might not be the result, or maybe the scientific theories might deviate from this. Or might differ in what they are saying or what they are describing. And I think this you can also see, for example, in the 1900s, there came about in philosophy, there came about ideas of superhuman. This was an idea that basically Nietzsche really was fond of this superhuman who will be beyond all the borders that society will put on him. And there was another philosophist who basically believed in another philosopher who believed in a class struggle, which was of course Karl Marx. And these two, if you look deeper into it, you see that they are closely related to a different scientific theory that arose in those times, and this was Darwin's theory of evolution. And of course, the Darwin's theory of evolution has a scientific basis. So I would say microevolution is pretty much established by now. What I mean by microevolution is basically the fact that there are mutations occurring in nature that lead to some living beings being more adapted to their surroundings just by the randomness of the mutations that occur. And these random mutations, if they randomly are preferable or are better for surviving in nature, they get through of they survive better than the others, and therefore this living being has better chances to survive, which is basically Darwin's theory of survival of the fittest. But I think up to now there's no clear evidence. There is evidence, of course, but I think you could not clearly say that it's already also happening on a macroscopic scale. This is, of course, what Darwin's theory of evolution and the theory of evolution in general states, is that this is also true on a microscopic scale, that really living different forms of living beings evolved into each other, or from one state to from one mutual ancestor. So I think there are still what I read about it, there are still many problems with this interpretation. So therefore there is no, as I would interpret it, there's no clear saying that this is really a fact, but more than just a theory or even a hypothesis. But for the fact for microevolution, it's pretty well established. So there is, for this theory of evolution, there is a scientific basis there, but still it is highly influenced, as any other theory is, highly influenced by philosophy. And I think if you just look at the fact that Marx, Nietzsche, and Darwin were all contemporary, so they lived at the same time, you really get a grasp that they might have been influenced by each other. So the philosophy of Marx and Nietzsche might have influenced Darwin, and on the other hand, Darwin's theory of evolution might have influenced Marx and Nietzsche. Also, you see some differences. For example, Darwin's theory of evolution does not say that there is a purpose in this evolution. It predicts pure randomness. It basically states that it's purely random, where the philosophies of Marx and Nietzsche really state that there is some telos, some purpose in this in the world. So they also have differences in their philosophical assumptions, so they are not completely in union with each other, but to some degree you see that they are influenced by another. So if you look at Nietzsche's idea of the superhuman, this is clearly related to the theory of evolution, of survival of the fittest, of beings becoming ever better, so to speak. And it's also related to, I think, this survival of the fittest idea is something that Nietzsche also implemented in a way to mean, so at least as I see it, to mean that this is also true for humans, that they do not need to be constricted by moral laws or something, but just because they are better, they can also do as they like. So I'm really taking a broad assumptions here, but I think it's kind of what it was saying. And also, even if Nietzsche himself did not say it this way, it is the way it was interpreted by many also later, to horrible effects, of course. But this is what it shows, that philosophy and science are always influenced with each other, and there is this factor. And if the philosophy is bad or badly implemented, this can, in my opinion, lead to bad science. So here you have it also, you have this, that here it is the opposite, that maybe the science led to bad philosophy, in a way that you had this social Darwinism, where they tried to implement the statements of Darwin's theory of evolution to the social area, and saying that some people are above others because of this evolutionary thing, that they somehow interpreted some people as being evolutionary further than others, and so on. So this was bad philosophy. And so it was, you might argue, okay, this is not clearly in the science there, but I think it shows that the ideas were around then, and it shows that if there is bad philosophy, there can also be bad science, and vice versa. And it can be clearly the case that the science behind it has a clear basis in facts, that it is to some degree true, but that the interpretation of these facts, that this is already given by a bad philosophy. And if this is the case, then you might have the facts in the right order. You might be able to predict most of it correctly, but still you are missing something, and the philosophy behind it seems to be confirmed by the science that you have, and therefore this philosophy, if it is bad, gets more support, because science seems to be confirming it. And you can see this also in another way. So, for example, something that even where the philosophy was even longer in the progress of developing. For example, Jean-Jacques Rousseau was a French philosopher after the French Revolution. And he believed that our inner authentic self is really who we really are. So he called it this inner authentic self, or that's what it's often called. And it is suppressed or oppressed by society. And the goal of humankind is to get free from this oppression of our inner selves, from society, and express our true self. And this idea was also adapted by Sigmund Freud, who, as you might know, is today is considered today as the founder of psychoanalysis. And today, many of Freud's theories are considered to be completely wrong. but still some ideas have hold on to in our social imaginary, you might call it, so in our thinking of how the world works, which is not necessarily rooted in science or in fact, but some ideas that we have, some from things we are convinced of or we learn from our childhood on. And if you look deeper into the theories of Freud and into some ideas he had, you can see that some of this is still in our social imaginary, as I call it, or as it is called in one book I read recently. And what it's meant by this is basically the assumptions that we have about the world and nature and everything else that are in our culture, that everyone believes, that everyone is convinced of, without really knowing where it comes from. Maybe it comes, and oftentimes it comes, for example, from philosophers, from highly sophisticated philosophers or ideas, and without us having ever read them, we just are convinced of them because we get it through the media, through movies, through books, and without even knowing where it really comes from, we get those ideas. And if you look closer, you see many of the ideas of Freud, for example, are still in our social imaginary, and this even though the theories he had about psychoanalysis are by many, even especially the experts and the psychoanalysts today, are considered to be wrong. So what can we learn from this? First of all, the facts of the nature, the facts of science, they are usually firm. They are, you can believe in them, you can trust in them, but still there are systematic errors, statistical errors that play into this. So they are not completely certain, and especially with systematic errors, there's the case that they can really be underestimated. So because it's really hard to estimate a systematic error. So if you are not familiar with systematic and statistical errors, so statistical errors are basically errors who occur statistically, so randomly. So you measure the size of a sheet of paper or something. You want to see how long it is, and its length in the one point you look slightly from a side, and then you look straight at your measurement device, and then you get different lengths, and if you measure a lot of times, you get in the mean of the true value basically, but there are always different measurements or different results probably. This is those are statistical errors. Systematic errors are errors in the system, so you're not necessarily doing something wrong, but every device has a systematic error, maybe something that where the reason is that you cannot really measure this value properly because of some systematic effects or something like that. So those are really hard to nail down, and it's really often the case that they are overestimated, or more often than that they are underestimated. And this has led into problems several times. For example, when measuring the neutron decay, if you look at the data, you can see that this time of the neutron decay was at one when it was first measured, it stuck really at the same value, basically around the same value. And at one point, a collaboration had a completely different value, and from then on it went to this value. And this is because it was measured the first time with an high systematic error, and the other times too, but this systematic error was never observed. They never found it, or it took a long time to find it, because every time they were measuring it, and if they got the same value as the collaborations before them, they thought, it seems to be right, because they got the same value, and this confirmed it to them that this seems to be true. And this is what we call a confirmation bias. So they were biased by the confirmation of this other group that already measured it, and so it took some time until the measurement techniques were improved, and it really was observed, oh no, there is really, that the value is really at a different place. So from this you can see that even with facts, even with measurable facts, there can still be the case that a systematic error is highly underestimated, and therefore the value that is measured is not in the area where it is supposed to be and is not trustworthy. It's really hard to find out for which facts that this might be the case, or if this might be the case at all, since, as I said, systematic errors are really hard to nail down, really hard to track, and really hard to find out where they are and how big they are. So therefore, this is also a problem with facts. But other than that, you can really believe in facts, can really trust that they are firm, that they are possibly true, but still this does not give you a theory. Facts don't give you a theory. You have to have this interpretation of the facts that is basically the theory, and this is already always depending on a philosophy. It's always depending on the philosophy or the worldview, or how you want to call it, that you have, and this will always affect the interpretation of the facts that you will yield. And this is, in my book, I state that this is depending on the worldview of the scientist who comes up with this theory. But more than this is not only depending on that, it depends on also the world in which he lives. So as I have stated, the philosophies that are going around in the ether, so to speak, they really affect the thinking of everyone in this area, in this field where these philosophies are shared, and also the scientists who's doing his experiments. So you might be able to separate, to make a clean laboratory where you separate every thing of your experimental setup from outer influences like radiation and so on, but this is already hard for the factual side. Therefore, you have systematic errors. But even harder. It's even harder, and not even harder. It's just impossible to separate the scientist from his own thinking, from his own philosophies, from his own worldview in interpreting the facts that he observes. And therefore, philosophy or worldviews will always play a key role in the theories that are being created. And this is really important to know, that you know when you are confronted with scientific theories, new scientific theories, but also the one that are currently existing, that are considered to be confirmed or considered to be fact, that there's always this effect that the philosophy of that's around, that's in this social imaginary, as I define it, that this is always affecting also the scientific theory. And this is really important to know, to really understand the scientific discoveries, and to really understand it, and also be able to distinguish it, be able to get it in the right view. And even especially as Christians and as believers, if we are confronted with scientific theories who seem to contradict the existence of God, you really can oftentimes ask, okay, is this really in the facts? Is this really in the scientific facts that we observe? Or is this due to the philosophy that is around, especially in those circles, that is pretty atheistic, that is pretty agnostic or even atheistic, and that generally does not believe that there is a God, or that there is a personal God who created the world as it is. But on the turn side, this also means that good philosophy will lead to good science, or a good and true worldview will lead to good science. And this is also one of the visions of Sci-Faith, to really encourage scientists, especially Christian scientists, to do science on the foundation of faith, because I'm convinced that this will bring the best science. It will bring the best scientific results. It will lead to the best interpretations of the facts of these findings, and therefore to the best theories. So if we really do get the correct interpretation, or the correct, let's say, the correct philosophy, the true worldview, then we can really get this lens, the right lens, basically, through which we can look at the facts, and then we can see how they connect to each other, and how they can be interpreted to in a theory that is really powerful, really making good predictions, and making also many predictions that can be confirmed in experiments. And therefore I think this is really promising to do science on this foundation of faith. And I think there's also evidence that this really seems to work, because you have, as I mentioned, you just have to look at the beginning of the scientific method, which really ushered in this scientific revolution. And if you just look at the scientists who were behind this, Newton, Kepler, and many others, you will see that they really believed in God, that they had a firm belief in God, and you will also see how this faith affected them in their thinking and in their interpreting of the facts that they observed. This you can, as I mentioned, especially see with Isaac Newton. And therefore, I think if one does this science on a foundation of faith, and really reaches out to get a true worldview of the world, and to look at the world through this lens, and interpret the scientific facts through this lens, then I believe one can do the best science, one can get the best theories, and therefore this is, I think, a really promising approach to use. Episode 24, Myths and Facts. So if you look into history and also everyday life, and everywhere you learn something, or you tell something about things, or about things you learned, you will realize that they are oftentimes told in stories. So they are oftentimes told through stories, narratives, to things someone experienced, through anecdotes, and so on. And this shows you that we understand the world through stories. So basically, if you experience something, you made some observation or something, you usually tell your friends or your relatives, or whom you tell them about it in the story in which you experienced it. You said, hey, I was going down the street and I saw this and that, and then I thought of something like this. And you won't tell him, hey, this fact is there. So usually you won't tell them this and that fact, this statistic, I made this observation using this statistical tool set or so. So if you're not a complete nerdy physicist, you probably won't do it like this with your friends, but you will tell them the story. And even in physics, even if you study physics, if you begin to study physics or math or any scientific field, you really soon begin to realize that even there you do it by describing things in stories. You only don't call it that. You call it examples. You call it something like that, because it really helps to understand even the physics and the maths of something by using examples. So as you can see from there, at least as humans, we understand the world in stories. And that's also the reason why throughout history we told wisdoms and so on were given on in stories or also myths. So that the many societies or many cultures have their own creation myths. So either a creation myth of the story of creation, and or myths in of how this people came to be, how their country was founded. So there's this, for example, this creation myth of the United States, for example, and here you already see that I don't use the term myth to mean a story that is completely invented or something. It surely has a historical core in most cases, or it can even be completely historic, but still I by myth you mean basically that a narrative that is portrayed brought through the generations with which people relate to and so on. So there are approaches to interpret this. So how can we see this, that these stories that we tell about each other, these stories that religions tell about their faith. So even if you also look into religion, if you look into the Christian faith also, you see that the Bible basically it tells a lot of stories. Also there are also proverbs, there are also psalms, and there's also this, but a lot of the Bible is really just stories, and the truth that comes through the Bible comes through those stories. So the thing is really, the question is, okay, how do we go about this? How can we interpret this? How can we use this? And what can we make of this? And there's basically one, I would call it a materialistic approach, and then there's another approach that I already mentioned, basically. But the materialistic approach, which is especially brought forth by someone called Yuval Harari, who writes in his book that I think the book is A Short History of Humanity, and in it he basically states that all those stories, all those myths, they are just that, stories, myths, constructs, just made up things that help people to bind together. So he uses this example of the car Peugeot, which is a French car manufacturer, and it's named after its founder, who was also called Peugeot. And he says that this brand, this Peugeot brand, this basically does not exist. I mean, the cars are there are the manufacturing halls, but basically it's just a made-up story. It's just something that made all these people come together and work together on this car and buy this car and so on. And that's basically what he says. It's just a made-up construct. But I think already here you see that he misses the key fact that these factories do actually exist. And also the cars do actually exist. So in a way, what Peugeot stands for does exist. And I think that's also what you can see in the stories, in the fact of stories. They convey something that is actually true, that is actually there. So as this brand of Peugeot actually conveys something that is actually true, that is actually there, that actually can be materialistic. You can touch this car, you can drive this car, you can really see it. You can see these factories, the workers, they get real money for what they do. So there is some truth portrayed in this brand, and in a similar way it is the fact that these myths and these stories, they really convey a truth, and this even if the story itself is not true in the sense that it is 100% historic. And we want to try to look at one of the basic myths of Western literature, to just see how this works out there. And this is what we want to look into is the Iliad, which is written by Homer. It's many say the oldest piece of literature of Western literature, and it is about the Trojan Wars. and especially about the conquest of Troy by the Greeks. And the story goes as such that there is this king of the Greeks, basically Agamemnon, he's called, and he is on his way to conquer all these city-states in Greek. And his brother Menelaus, he's trying to work out a peace treaty with Troy, and this seems to work out perfectly. But the son of the king of Troy, Priamos is the king of Troy, and his son, one of his sons, Paris, he falls in love with the wife of this Menelaus, the brother of Agamemnon, the king of the Greeks, and this is Helena. And he falls in love with her, and basically when the Greeks are leaving Troy after they signed this peace treaty, he keeps her with her, and as soon as Menelaus notices that this has happened and they don't want to give her back, then he and Agamemnon basically declare war on Troy, and this is a pretty tough war. It goes on for 10 years. And what's happening there? So the Greeks have their great hero, their great war hero is Achilles, and he in the beginning is involved in this war, and he takes from the Trojans, he takes Briseis, a girl, a peasant girl, and he takes her into his tent, and Agamemnon, he has so the king of the Greeks, he has an issue with Achilles. They don't get along very well, and as a show of force, basically as a show whose boss, he takes this peasant girl from him to himself, and then from then on Achilles is angry, is in anger, and he refuses to fight for his people, and therefore, because he's missing on the battlefield, basically the Greeks taking hard defeats, because the Trojans, they also have a big hero. This is the other son of the king of the Trojans, of Priamos, and this is Hector. And he's really giving it to the Greeks, basically, and then they try to convince also Achilles to join the fight, to reconcile with Agamemnon, but he refuses, and so they are in this situation. And then the friend of Achilles, Patroclus, he decides to join the fight, and he uses the gear of Achilles, and therefore he looks like Achilles in the fight. And Hector, assuming that is Achilles he's fighting with fights Patroclus and kills him, and therefore Achilles is now angry with the Trojans, especially with Hector, and more angry than with Agamemnon. So they decide to reconcile, and he challenges Hector for a fight. He kills him, and as a sign of humiliation, he puts his dead body on his chariot, and every day he rides with it around the walls of Troy. And this leads his father. So you have to understand, for the Greeks, the honoring of the dead was really important. To give them a proper burial and so on was really important, also because they believe in an afterlife, such that they need to give them a proper burial for them to go into the afterlife or something. I'm not. I also don't know a lot about it, but it's really. As for most people, it's really important to them to give them a proper burial, and therefore this King Priamos comes into the camp of the Greeks without being noticed, and he comes to Achilles, and he begs him to give him the body of his son Hector, to give him a proper burial. And Achilles is kind of moved by this and decides to not only do that, but also to give them time in their fight. So they basically basically agree on a ceasefire where he will not, the Greeks will not attack them for the time when they are grieving their son Hector Day. So they have basically their set times in which they will do it, and in this period Achilles agrees that they won't attack them, and so it ends pretty peacefully as it seems, but if one knows the complete end, which is not included in the Iliad but in another work of Homer, then you will see that in the end, I mean, most of you I think know the story. The Greeks start to play a trick on the Trojans by basically acting like they would leave, and acting like they would leave behind some present, some great horse that they built, and the Trojans basically bring the horse home into their inner walls, and surprise, surprise, in this horse there are Greeks hidden in there, and in the night they get out of there, open the doors, they open the city gates, and Troy is completely destroyed. So this is the story, and what I mentioned now only already was just as you might have called it, the not probably, but the part that could be historical, because if you read the Iliad yourself, you will realize there is a lot of other stuff in there about the gods who turn sides on who they are supporting, if they are in favor of the Trojans or in favor of the Greeks, and how they fight among each other and so on. So Homer really paints this picture that this is basically only the chessboard of the gods themselves, who just play around themselves with the fate of these two people. And this you can, as you have noticed, you can basically tell the story without using any of this Greek mythology, of their gods and how they play along, but Homer tries to tell, of course, something with this. He wants to use this as a symbolic way also of showing who, if someone is in the favor of the gods, he's kind of maybe also expressing who in this situation was on the right side, or rather on the wrong side, and so on. So he uses this in some kind of way, and I think even for the Greeks at that time, they really, of course, believed that the gods were to some degree involved in all that they are doing. So their gods that they created, they had, and that they were involved in all these kinds of things. And for them, this was really how they might have thought that this would have happened. And this is just a myth in this classical sense, in the sense that you might say, okay, there might be a historical core, but probably not everything of it is true. And most certainly the background of these gods having their way there is not the true story. And for a long time, this was really considered a true story, so a completely true story. But then it was doubted, and then it was even doubted if Troy exists at all, until some archaeologists just tried to find it, and indeed Troy could be found in modern day Turkey. But it is still there are still people. Or it's still in an open discussion if the Trojan War really happened, or if it happened in this way, or in which way it happened, what key facts of this Trojan War are really historic and which ones are not. So there's still an open debate, and there's still no clear answer to this from a historical side. And I think the truth might lie somewhere in between that. So probably this love story of Helena and Paris was not the trigger of this whole war, because to fight for 10 years just because of that would be a little bit rough. But also it might have been it might have been a reason that was stated, but not the reason, or something like that. And different things might not be completely accurate, and there might be some exaggerations, some things that came into it, or that were told about it that weren't actually true, or that stemmed from other stories. So I think you can assume that there is a core truth to it, an historical truth to it, and that is really happened this way. But even if you do not believe that, even if you believe this is completely made up and Homer wrote it down or invented it, or in his the culture he was living in, those were the stories they were told and he wrote it down, but they were completely made up. Even if you believe that, then there's still the fact that this story conveys some truths that the Greeks were convinced of. For example, the Iliad has as a central theme, it has the theme of anger. So you see Achilles is angry with Agamemnon because he took his girl away, and later he's angry with Hector because he killed his best friend, and in his anger he's going pretty far. So he lets his own people take crass defeats against the Trojans, just because, and doesn't let go of his anger still, and he also humiliates the Trojans in a hard way, just because he cannot let go of his anger of having lost his friend. So this is the central topic of the story, and if you look at the fact that is even more than 2,000 years afterwards, far more than 2,000 years after it was written down by Homer, people still read it, people still talk about it, people still make it into movies, then you might realize, okay, there seems to be some truth that is portrayed in the story, that it even today, even now that the Greeks, or those Greeks, the ancient Greeks, are far gone, even today we still discuss about it, or we still read about it. So there might be some truth that is conveyed in it. Otherwise, why would we do that? So I think that's the big question you can ask if somebody says, yeah, those are stories that they are just made up, they are just invented. Then the question is, why do people care about it? If it's just something that was invented without any correspondence to some truth or to some real thing, then why would people care about it? And I think that's where people who say that it is just invented and it has no meaning at all, where they are completely wrong, because then nobody would care about it. And the fact that people care about it, the fact that people are interested in it, the fact that it touches people's lives, shows that there is some truth conveyed in it, and it also shows the power of story, and it shows that that stories always convey some truth, and therefore it is that they are really important. I mean, you can, for some reason, to some degree, you can see this also in physics. So I mean, or let me say it like this. So you have some stories who abstract something. So for example, the story of the Iliad, it abstracts some parts of this maybe historical event of the Trojan Wars to focus on this issue of anger. And in the same way, in physics, you might use everyday examples, but you extract them in a way to focus on the physical phenomenon you want to observe. And there you have exactly the same thing. You might know from your math from school, from your math tasks, where you had these examples of somebody buying 1 billion melons or something, where you think, oh, that's completely crazy, who would do that? But it's an everyday example in the sense that in your everyday life you go to the store and buy something, but you abstracted it in such a way that it might not be an everyday example anymore, because you buy a bunch of melons that you couldn't consume in time for them before they go to waste. So there is again the fact where you see that there was something abstracted, and then it might not be the complete truth anymore in the sense that it really happened, but it still conveys some truth. And this you have, as I showed also in science, and you have this in stories. And therefore it is in this regard important to find the right interpretation. And this is important in physics. You need to, if you have these examples, these physics examples, of course you have to know that this might not necessarily be the things that are really happening, but they are to show you something about things that are really going on, these examples. And in the same way, stories are not necessarily in every case historic events, but they show you something about a truth. They show you some truth that is contained in them, and that's why they resonate with you. And so in scientific theories, you can also see it like that the theory is basically the story that the facts are telling. So we had it also in the last episode. We were talking about facts and about the philosophy with which we interpret those facts. And there you can see it also that the facts are telling basically a story. They conveying a truth that you want to find out. And the theory is basically a try to grasp that truth, try to get this truth out of the facts, and to get basically the story out of the facts, to get the story that the facts are telling out of it. And this is also a way in which you can see that. And you might now think, okay, as I said, we talk in stories, we think in stories, and if you also look into the world, if you just ask a politician what he uses in his speeches, he will soon tell you, yeah, I don't use so much statistics, but rather I tell a story that uses some of these facts in the statistics, and because that resonates better with the people. And you might now say, hey, at first you might think that's bad, because then you need to tell some story or something, and why cannot people just accept the facts? Why can we not give them the facts and they accept it? It might be easier it might seem easier this way, but you have to also understand that this way you can be easier fooled, because facts can, if you just get presented a fact, you have no knowing of whether this is the truth or not. It's just a fact. It's just something. Nothing resonates. Nothing. You get no intuition about it unless you are really an expert on the field, and you might have an intuition of some fact, of course, if it's accurate or not. But if you're out of the field, then you probably don't have this intuition, and then with a fact you don't really get much of an idea of what this could mean. But with a story you might have this sense of, hey, can this be the truth? Because there's something that resonates with stories. And of course you can be fooled in there too. So there are also stories who portray something that is not true. There are many stories who portray something that is not true, but even in those stories there's some truth that is conveyed in it that is then oftentimes perverted, and in a way tries to turn this truth around. So in general, you can, I think, say that stories work much better at conveying truth, because it's a lot harder to fake or to fake a story, to fake something into it. So to make a story compelling and carrying something that resonates with people, and for it to be completely untrue. You see this in, if you just look into the movies and so on, you see that when it's not authentic, when it doesn't seem real, you see, okay, there's something off. You do not even have to think a lot about it. You just realize something's not fitting there. And with stories you can also get it. If a story is not realistic, you just by your gut you already realize that, and therefore you can much better distinguish their truth from untruth. Still, you can, again, as I said, you can manage to get untruths into stories, but it's easier to detect them there, and even the harder it is to detect them, the more often then there are some truths contained in it that are then turned around in some way. So what's still I think as I said, stories always contain some truth. And even if the story is not itself historic, it contains a truth that makes it resonating. But still, if for the complete truth, for a story to convey the complete truth, logically it has to be absolutely true. So I mean, if you have an absolute truth, something which is completely true conveyed by a story, then this would necessarily mean that the story itself has to be true. It has to be historic. And that's why I also believe that the Word of God, since I believe it is the absolute truth, has to have also, so that the stories of the Bible have to be actually true stories, historic stories. And I think especially in the case of the Gospels, this has to be the case. And there, as I as we had it in one episode regarding the resurrection of Jesus Christ, where this is really necessary for the Christian belief to be an historic event, and where I talk about this really being an historic event. So if you want to, if you are interested in this, then I really recommend to listen to this episode to see where the facts lie in this, and that there is an actual factual basis for the resurrection of Jesus. So I hope you could understand this point, and I think, as I said, it's easier to distinguish truth from falsity in stories than in just stating facts, especially if you're not an expert on the specific field. And there's also there's also still, you need to filter this story to get the truth out of it. So of course, if you have a story where you say, okay, it's not the complete truth, but it conveys some truth, then you need, of course, be able to extract this truth from it. And for this, you need the right lens to look through it. And this lens should be the lens of the truth. And for Christians, it's clear what this is. This is the Word of God. So if we look at for example, if I look at a story, then I look at it from the lens of the Word of God to get the truth that is out of it, that is in the story. For example, if you are familiar with the book tweets I'm doing on Twitter, there I really try to put out those the books I'm reading, and I really try to extract the truth out of there from looking from the Word of God. And the other approach to do this is from ideology. So, for example, materialism. And this, we also talked in the episode before about these philosophies, and this in this case, the philosophy of materialism, and this author I mentioned, Yuval Harari, who said the stories are basically just made up stuff. He also comes to this with a materialistic approach. But the problem with that is that truth cannot contradict itself. That's just if there is truth. So if you just for a second assume that there is truth, then it cannot contradict itself. So that's what you mathematically would say. It has to be well defined, and well defined means it has to be existing. One point of being well defined is to really be existing, and the other would be to be unambiguously, but to be existing so is being well defined. And so it cannot, something that contradicts itself cannot exist, basically, because it contradicts itself. And the fact is that materialism contradicts itself, because materialism is an immaterial idea. So materialism states that only the things that are material can do exist. But materialism is itself an idea, and an idea is immaterial, and therefore materialism could not exist if materialism would be true. So it contradicts itself, and therefore it can actually not be true. And as you see, I think if you dive deep into what Yuval Harari tries to say in his book, you really get to the conviction that he not actually believes that there is something like truth. And that's also this postmodernist idea that there is no truth. But then, I mean, this contradicts itself also. If there is no truth, how can you know that there is no truth, or how can this be true? So if you really just assume that there has to be something that does not contradict itself, and this is what you would call truth, then all these ideas that are floating around there just don't work anymore. And so I hope I could make it clear to you that why I believe that stories are important, and that why I believe stories have been important throughout history, and why stories in many ways are more effective of making people able to distinguish the truth from things that are not true, because they resonate with us, and from this resonance we can really distinguish the things to be true or not true. So that's everything for today's episode. I hope you liked it and you enjoyed each part of it. If you want to get in touch with me or discuss a topic or want to give me some feedback, then feel free to contact me using the contact form on my website, sci-faith.de/en. And there you can go to the contact tab and contact me. And if you have any other things or episodes you want to have covered there, or topics you want to have covered, feel free to contact me there. Also, if you are not yet familiar with the format in which this podcast is produced, let me just briefly explain it to you. So there is always at the beginning of a month or of a block, there is a big block of 4 episodes in one thing. It's kind of like a preview, which I call it, where you have the next 4 episodes all in one episode together, combined. And this is for people who like to hear long format podcasts, who have a long way to work or something else, where they can listen to a long episode and can then have a preview of the next 4 episodes all at once, and are completely up to date from the beginning of the block. For those who like their episodes shorter, who prefer it if they have a half an hour or even less of a podcast episode, for those there is every week afterwards will appear a podcast episode almost in that length, and this way I can publish every week a new podcast every episode, and everyone can have it his own way, either once a month a long chunk of content, or once a week a shorter format podcast episode. So I think that's the best way for everyone, and also for me when I'm producing it. Please also note that this is an independent podcast, which means that it is recorded, produced, and marketed by me. So I really need your support in this. So if you like this podcast, then give it a 5-star rating. And if you have the time, even write a review to it. This just helps other listeners to become aware of this podcast. And then people who might be interested in this content can become aware of it. Also, if you have friends who you think would like this content, then recommend it to them and share it with them. Also, you can support me in other ways, for example by reading my blog and subscribing to my newsletter, or even by reading my books, which you can find on Amazon. For example, there is my latest novel out now is Alien Thoughts, which is pretty entertaining from the feedback that I gotten, and so it's also in some way related to science and faith. The topic of it is also in there, but of course you can also read the book to this podcast, Sci-Faith, The Compatibility of Science and Faith, which is also available in English since last year. Thank you for that, and now I wish you a wonderful day, and I'm looking forward for you to tune in again next time.